So the first thing I'm going to say is that some of the things I'm going to be talking about are going to seem a little bit science fiction-y. I'm going to be talking about metals that have no resistance. I'm going to be talking about things that are cooled down to 10 thousandths of a degree above absolute zero. So just in case you're interested, everything you'll see and hear from me today is backed up by references we have publicly on our website. So you can actually go and read the research papers, see the results, and try the system out for yourself after hearing this talk. Let me begin by saying that the growth in the computational ability of the technologies we have around us, it has been exponential for a long time. It's referred to as Moore's Law. And these days, there's emerging a Moore's Law about Moore's Law, which is that the number of people who are predicting the end of Moore's Law is doubling every 18 months. So I'm not going to make that mistake by saying, oh, Moore's Law is done, and there's going to be no scaling of classical technologies now. But we have seen that as the technologies have been developing, their growth rate has been slowing. Now, the interesting thing about quantum computing is that's often referenced as a need for new computing paradigms, but with quantum computing, that's not a necessary hypothesis at all. Quantum computing has a feature where the complexity of the problems it can approach grows exponentially with its scale, which means that if the technology is scaling exponentially and the problems are scaling exponentially in difficulty with their size, then you have the potential for super exponential growth. So that's the reason why quantum computing is so alarming in its immediacy. And a lot of the folks that I talk to are interested to know, how do I get access to a quantum computer? What kind of problems does it solve? And where is it going to affect my business applications or my government mission or the research that I intend to do? So let's try to make quantum computing a little bit tangible. It's often a very abstract concept. So this is a photo of a DWave 2000Q quantum computer. It's about 3 meters by 3 meters and 3 meters tall. So it's quite a large system. Inside that large room is an ultra-cold refrigeration system, which is featured, we have it right here. And down at the base of that ultra-cold refrigeration system is where the quantum processor is, and that's blown up into this large figure here. So when I say ultra-cold, I mean that if room temperature is basically the temperature of this plate at the top, then in the middle here, we're looking at the temperature of interstellar space, about more than 100 times colder than that. And then down at this base plate, the temperature is another 100 times colder. It's at 10 thousandths of a degree above absolute zero. So cold that if this were ever to occur in space, it would immediately get warmed up by everything around it, just like the background radiation of the Big Bang. Now, the other thing I'd point out is that a feature of what I'm going to be talking about today is energy consumption and computation. It's a very talked about topic in high-performance computing these days, and that's because if you look at a high-performance computing cluster, these racks are what you commonly see housing all of the different computers that are used there. And one of these racks in a high-performance computing cluster would not be uncommon for it to consume 100 kilowatts per rack, whereas this entire system here consumes peak power 25 kilowatts. So it's significantly lower power consumption than a high-performance computing cluster. Now, if I were to take the cover off of this chip packaging and show you the quantum processor underneath, then this is what you would see. And for those of you technologists and computer scientists and hobbyists at home who have taken a computer apart and looked at, what is the computing chip there, will begin to feel more familiar to you because, because CPUs and GPUs are also fabricated on silicon chips in the same way that this quantum computer is. There are some, however, really important differences. One is that the metals that are used to carry the currents on this chip are made out of materials like niobium, and when you cool niobium down to these ultra-low temperatures, they superconduct, which means that they can flow currents without any resistance whatsoever. This would be like turning on your light bulb and no light comes on because there's no resistance in the wire. So this has a really key feature, which is that when this system is in operation, and this is performing the compute. This quantum processor unit consumes 1/10 of a billionth of a watt. So it's, in a very transformative way, breaking the relationship between computational power and the energy consumption we're used to with classical computers. Okay, so what are we going to use a quantum computer for, and what can it do for us? A common mistake would be to assume that as quantum computers develop, they're going to replace classical computers. And I can tell you that's definitely not going to be the case. And the reason is because classical computers have had 70 years to develop. And there are certain computations and calculations that they do exceptionally well. There's no way for a quantum computer to catch up to general computation in that way. However, what we've seen in the quantum computing systems that we've been building and providing to our customers is that they're incredibly good at searching vast landscapes of solution spaces. So when you're programming a quantum computer like the ones that DWave has commercialized, you're casting your problem as an energy landscape which has lots of peaks and valleys, and it's extraordinarily large. And the quantum computer is going to find for you the lowest valley or valleys in the landscape and then tell you where those are. And the way it tells you is that the coordinate space of the landscape is the basic bit values you get out of a quantum processor, so a series of zeros and ones. A classical computer is going to approach the same types of problems by trying to run through the landscape incredibly quickly. It will use a particular strategy, maybe like downhill run, to try to step through points in the landscape as quickly as possible and try to find the lowest point or points that it can. And classical computers can do that incredibly quickly. They can sample 5 billion points in a landscape like this every second. But some of the landscapes I'm talking about, if you had, let's say, a processor with 300 bits in it, the number of solutions in that solution space is roughly equivalent to the number of particles in the universe. So 5 billion samples in a second is like a tremendous undersampling of the overall solution space. And with the 2000 qubit technology, those solution spaces are as large as 2 to the 2000. So much, it's one of those numbers that's so big we don't really know how to sort of conceptualize it. Okay, so that's the concept of programming a quantum computer and putting it to use for you. And this is the actual equation of what the quantum computer is doing. So I've included a lot of information here, which is talking about the fundamental building blocks of the quantum processor, the quantum bits. So these are the memory elements that can store like a single bit of information, a 0 and 1. And also physical devices for coupling those qubits together so that they can actually influence each other's states. But I'm not going to focus too much on the formula. This is sort of the only formula that's in the whole talk. But the nice thing about this formula is that we can effectively read it out in like an application context to kind of make it feel a little bit more familiar. So that's what I'm going to do. So this OBJ represents an objective. And I'm going to talk about this in terms of finance. If our objective were to optimize a financial portfolio. So if my objective is to optimize a financial portfolio, I'm going to need to provide some information, A and B here, about the commodities markets. That information has to go into the quantum computer, and then the quantum computer is going to pass out a series of qubit values, which are all 0 and 1, and that's going to tell me which assets I should be selecting and which ones I shouldn't be selecting. Now, the way I pass that information in is that I say, the selection of an asset, I want to weight it based on what I think is its expected future value. I want to weight the selection of assets preferentially for things I think will have higher value in the future. In addition to that, I also want to take into account the correlation between assets. Because the whole purpose for pulling together a portfolio is so the individual assets will balance each other out to the volatile pushes and pulls that come from the marketplace so that the growth of the portfolio will be more steady. Less volatility in a financial portfolio corresponds with less risk. And that's it. With those two terms, the weighted selection and the correlation between assets, we've just created a fundamental instruction for a quantum computer. And for people who work in finance, that's a very familiar problem form. They program like this every day. That's referred to as preparing a covariance matrix. So for those of you in the finance industry, that might be a very familiar term. For those of you who work in machine learning and artificial intelligence, there's also problems which have exactly the same form. These are often considered the synaptic weights between neurons in a neural network. And you might set those weights to then determine, we'll have questions at the end. So the question was, can I repeat what A and B mean in this context again, in the context of neural networks? So in this case, A would then be the weighted likelihood of the neuron firing. So potentially a neuron has a higher likelihood of firing, or if it's evenly balanced, if it's like a completely even-sided coin, then this coefficient A would be 0. And B then is a synaptic connection, an undirected synaptic connection between two neurons. So if one of them is firing, then depending on that coupling weight, it might either suppress the other neuron or it might activate the other neuron. So those are the synaptic weights between the neurons in the neural net. So for some groups of people, if you're in physics, this is an Ising model. If you're in computer science, this is often referred to as a QUBO. There are a variety of different names in different fields for this kind of programming model, but it's very basic and fundamental, and it's very common in a variety of applications. The difference between this and what you would get with a classical computer is that the basic operations of a classical computer are addition and multiplication. So every step you would want to take in the search space requires you to take this function and break it down into a sequence of addition and multiplication steps. And if you want to take a particular solution and evaluate it, you can see that I have multiplications here and I have additions. So the evaluation of a solution is very fast. But the solution space is so enormous. We have to do such a large number of evaluations. That's what makes this problem very difficult to break down for a classical computer. So let's talk about relevance to today, right? This is the Quantum Futures the Futures Technology Conference. So where are we in the life cycle of quantum computing? Well, in 2004, DWave was working with sort of 1 and 2 qubit devices. And then in 2011, we sold our first product, the DWave 1, with 128 qubits to Lockheed Martin. 2 years later, we quadrupled the size of the processors, and we sold one to Google and NASA and the University Space Research Association. And then after that, we sold a 1,000 qubit machine to the Los Alamos National Laboratory. And so on and so forth. We've been moving up the chain, further increasing the levels of integration in quantum computers. So now that we've talked about the size scale, what does that actually mean relative to performance? So I'm going to try to sort of highlight some performance benchmarks that have been done in the system over its history. Down at the 16 qubit level, or sorry, the 4 qubit level, these types of calculations can be done on pen and paper. That's often how we verified how the machine was working. Once you get up to 16 qubits with 2 of the 16 possible solutions, then you're starting to get up to an Excel spreadsheet. Now you actually want to keep track of quite a large number of solutions. And once you get up to 128 variables with 2 to the 128 solutions, we found that commercial software could obtain solutions to these problems faster than the quantum computer could, roughly around the time that we were selling our system to Lockheed Martin. The interesting thing is that by the time we got to the DWave 2, we were 10,000 times faster than that commercial software. So we saw a huge increase in the performance relative to that software called CPLEX, and that brought a lot of researchers into the field who were then saying, wow, okay, let's start looking at performance benchmarking for problems of this type, and let's start developing some very, very competitive heuristics that are trying to compete specifically with the quantum computer on the problems that it solves. And when they did that, they managed to develop hardware-specific code for simulated annealing that could attack problems and match the performance of the quantum computer when we had the DWave 2. Now, at the end of 2015, Google, using our 1,000 qubit machine, famously demonstrated a set of problems for which the quantum computer was 100 million times faster than simulated annealing. And by the time our 2,000 qubit system came out, there were some researchers at Texas who by that time had developed an entire suite of different heuristics. And they tested some problems against the entire suite of heuristics and were able to demonstrate that every single one of those heuristics could be beat by the quantum computer. So what does that mean about the direction of quantum computing? Well, we're going to be moving out of the space of competitive synthetic heuristics, and working on increasing our commercial relevance. Nobody is going to be doing a benchmark demonstration bigger than 100 million times advantage. And the reason is because you have to spend 100 million times longer running your classical computers to make that comparison, and that's way too expensive. So what we want to do is we want to be applying these to business problems and to mission problems and really putting them to use. Because what our goal is to take quantum mechanics, sort of the weird fundamental properties of the universe, and then apply them to do useful work for us. When I was at the supercomputing conference last year in 2017, I was at a conference session about other types of computing technologies, and somebody presented this stack and said, we're looking at different computing paradigms for quantum computing. What is it that's changed? Are the materials changed? Yes, they definitely are. They're superconducting now. Have the devices changed? Yeah, the basic memory elements can now be in superpositions of states. They can be in zeros and ones at the same time, so dramatically different from what you would get with classical computing. The logic is fundamentally changed. Even the computing architecture has changed. The quantum processor is like a classical quantum hybrid, and its memory register is quantum mechanical. But despite all of those differences, what we found was that the algorithms were actually very familiar. The way you would specify your problem to the system was familiar to a large group of people, which meant that this was the entry point for their application workflow. This is where they would take their software down to some particular familiar algorithm like simulated annealing, and then instead of putting it on a classical computer, they would pass it to a quantum computer. So that brought us to the point of really helping to frame the programming model for a quantum computing system, which is that considering it as a sampling engine that you access as though it were an algorithm. And it's a co-processing resource that you want to use asynchronously. You don't want to send a problem to the quantum computer and then wait until the answer comes back. You want to be doing multiple things at the same time. And the primary challenge in programming the quantum computer is in specifying the problem, casting your problem as that energy landscape. Over the last 8 years, we've been working with a variety of customers all over the world, and they've been developing a variety of applications. There's actually 100 early applications for quantum computers now. We had our user group meeting in Knoxville, Tennessee earlier this year, and to see people talk about the financial portfolio example I was discussing earlier, and machine learning and tsunami evacuation protocols, a wide variety of applications. And the reason I bring this up is because as diverse as this set might be from optimization, machine learning, and quantum materials, what they all have in common is that machine instruction that I showed you earlier. A problem where they need to sort out a model of correlated binary variables, and they need to optimize those in order to proceed with their application. Now, one of the fun things about working with DWave is that especially having been there for 16 years, is that we're now working with systems at a significantly larger scale. We're not working with a dozen devices anymore. We're working with thousands of qubits. And so we've actually done 2 studies which concluded this year, which got published in the journals of Science and Nature, looking at quantum material simulation. And the paper that was published in Nature was to do with topological insulators and the theory of topological phases of matter, which is what Dr. Michael Kosterlitz won the Nobel Prize in 2016 for with Dr. Taulis, pardon me if I'm mispronouncing their names. And the interesting thing about this is that this quote that Dr. Michael Kosterlitz provided us. So this is a system in 2016 where the Nobel publication about it said, the race is on for the discovery of new exotic material phases of materials. And 2 years later, we were actually able to use a programmable quantum system to actually demonstrate that you could evoke this material property in a quantum system. And so in the past, these kinds of studies, like the one that we published in Science here, these were done with high-performance computing systems, SGI or Cray supercomputers in the late 90s. And in the future, these types of studies will only be done on quantum computers because it's so much more efficient to do them with a quantum computer than a classical computer. So when I'm talking with customers or people that I meet in business or people who are working on their missions, often the question they have is, what does a quantum computer do, which we've been discussing? And also, where is this going to be applicable in my business? And how is it going to disrupt my business? So imagine that you're working in a particular space like machine learning or AI, and at some point in time, you're getting better results with a classical computer. And then a short number of years later, the only way for solving that problem is incorporating a quantum computer. How is your workforce going to adapt? How are developers going to adapt to that and learn how to incorporate quantum computing in their applications? Oh yeah, that was the laser. So at DWave, our strategy to help answer those questions for our customers is to provide software tools that enable them to go through this learning process much more quickly. So they're benefiting from all the hard work of some of the visionaries who've been working on the system over the last 8 years. And this includes helping to highlight different optimization application spaces, whether it's traffic flow optimization or web advertising, or constraint satisfaction problems to do with scheduling or finding faults in electrical circuits, and then providing them with open source tools which allow them to automate the process of mapping their problems to problem forms suitable for a quantum computer, and then providing them with a suite of resources which is not just DWave quantum computers, but also classical techniques for solving the problems so that they can generate hybrid approaches, so they can get the best possible results today, tomorrow, and in the future as the technologies develop and change. So at the very top level here of this open source stack, users and developers can enter in with simple software commands. And then at the lower layer, that's where the translation occurs to these casting the problems as energy landscapes, so that users can use the tool set to help them with that process, or as they learn more about the system, they can actually dive into the open source software and begin making modifications and develop their own custom techniques. So at DWave, we recognized that we needed to provide access to the quantum computers. I would sort of present the view, this is my view, that part of the reason why quantum mechanics feels so strange to us, the idea of things being in superpositions or being entangled to one another, is because we never interact with them. We never get an opportunity in our daily life to interact with some system that behaves that way. And so there's nothing about it that we can form an intuition to. That's just not the way we only learn by interacting with systems. So we've actually created a real-time quantum application environment for developers to come and build and run their own quantum applications. And it's also a community with a lot of learning resources, because everybody who's coming to quantum computing, everybody I ever interview for a position at DWave says, I don't really know a lot about quantum computing. And that's our universal experience, right? That was my experience arriving at DWave. I didn't know a lot about quantum computing. So in this site, you can actually just sign up for it directly, and what you'll see is that you get immediate access to a quantum computer. You'll be walked through some illustrated demos, which can show you problems of different types, motivate them as sort of general optimizations, connect them to specific application examples, and give you the opportunity to actually execute problems on the quantum computer itself. We've also provided a variety of learning resources so that people can learn about quantum computing, they can learn about those early applications that have been attempted so far, they can learn about our customers' quantum application programs. Many of them have developed quantum artificial intelligence laboratories for studying what is potentially possible with quantum computers, and also published research. We've created illustrated demos to showcase small versions of problems. We've also created some interactive programming systems online. So you can go into your browser, read through an example, but actually run the code in your browser and then begin to explore the boundaries of your understanding right there. And the ability to then install the software development kit to begin developing or incorporating it in your research. But this is more than just about building a quantum computer. I'm not here to try to sell a quantum computer or to convince you that you need to be using one. But it is about growing an industry. It's going to require us to have researchers who are exploring the bounds of what quantum computers can do and learning what quantum physics can be used for in information processing. It's going to require companies who are building the hardware and commercializing it. And it's going to require people from software fields to come in and begin laying out common paths, tools, for people to begin to cast their problems and sort of see the different ways that quantum computers can be used in application. And so we've developed a set of community forums where people can participate and interact, where they can learn from the community and their common experiences, but also contribute their knowledge and their ideas to the community in order to really compound the rate with which we can learn. That's one thing we've learned from working with customers. One of the things we've learned from working with customers over the last 8 years is how much we all benefit from each other's common experience and learning quickly from both our successes and from our failures. And lastly, we've provided a help center here because, and this has definitely been my experience, it's actually reasonably difficult to find the resources that you're looking for. Sometimes you're looking for information about how the quantum computing system works. Sometimes you're interested in the model of quantum computation. Sometimes you just need help or documentation on software tools. So we've created a federated search tool here which operates over a knowledge base, but also a variety of other repositories of information related to quantum computing. So with that, I hope that I've managed to convey some of sort of the exciting developments that I've seen over the last sort of 10 to 14 years in quantum computing, and hopefully also interested you in learning a little bit more and diving a little bit more deeply in the future. Thanks very much.